So, well, hello everyone. So it is a pleasure to have Pavol Severa as our first speaker, and he will be talking about non-topological boundary conditions in perturbative Chern-Simons and AKSZ models. Thank you.
Thank you so much. Thanks a lot for the invitation. And I should apologize that this will be a little bit of a maybe physics talk by somebody who knows nothing about physics. So just be prepared. So I will start with Chern-Simons theory. Actually, most of the talk will be simply by Chern-Simons theory. So what it is about? It's Chern-Simons with a action functional. For somebody with a connection. Let's write down the formula. So three-dimensional. Unequal to M. And there are basically two approaches to this theory. One approach was to simply solve it, or define it completely, and which was done first. So it was the thing which was done by Witten. So let's call it non-perturbative approach. So what does it actually need? It needs a compact Lie group. So it's G is compact. We need to choose this pairing in sense of it's invariant pairing on the Lie algebra, right? One needs to choose the level or things like that. So there are some small technical issues. But then what we can found out about basically define the thing, what he related it to what is called the chiral Wessel-Witten model, which was something which was known by Witten in particular. But how does it work? This relation, this connection is by what is called the chiral boundary condition. So that's what happens when our M actually has a boundary. We mentioned that boundary of M is on surface, and we actually put a complex structure on sigma. Say our Riemann surface. The boundary condition says that when we take our connection, let's just imagine this one form as with values in G, that it's a 1-0 form. Sigma with G. And okay, so this thingy, which is a topological field theory, has this boundary condition which is non-topological. It uses evidently something more, and it produces on the boundary something which is not non-topological. It produces a conformal field theory, boundary conformal field theory, one should say. And that was and out of this, he was able to basically define everything over here. There is another approach which came just a little bit later, which is perturbative, which might look a little bit strange that if the thing is actually done perfectly, why to do it again imperfectly, but it always helps. So there we do not need a choice for compact Lie group. All that is needed is a invariant inner product on whatever Lie algebra. Actually, we do not really need any Lie algebra. We can just work with graph complexes or things like that. So it's basically when people draw kind of diagrams with trivial vertices that would correspond to the Lie bracket on G, That's all done completely abstractly. So these are just graphs, something of this sort. And roughly speaking, the way it's done, that we just need a propagator. Which is, let me say it in a way which will offend everybody in the audience. So the thing is that we need a homotopy operator. Somebody who will go from differential forms. Something of degree -1 and H. And for homotopy operator, I will just say that it satisfies that DH plus HD is equal to identity. Now, this is the thing that will probably offend many people. Like, what do I mean? How can the ground cohomology be ever zero? So let's imagine that everything is fine. One way how to do it is to do it around a non-trivial flat connection, and supposing that the corresponding cohomology is zero or something like that. But in the examples that you will see, this will actually be true with some correct boundary conditions. So don't worry about this too much. Otherwise, one needs to put here some projection to the cohomology or something like that. And then so this H is given by some integral kernel. Kernel of H that's going to be the absolute propagator, which is now a two-form on let's call it like this. Configuration space of 2 points on M. That's what that's n times M minus the diagonal. And with values in whatever endomorphisms of G, or I can write it just with values in G tensor G using the inner product. And which satisfies that PP, it's closed here, but it's supposed to actually give a ground current on n times M. So in that sense, dP is equal to the delta current on the diagonal times the inner product inverse or something. What does the one do? We mentioned that we have some graph with trigonal vertices. This is not trigonal. Okay, like this, and there might be some external vertices still. I'll show them like this. We're simply putting P on every edge. Now in every vertex, we're putting the structural constants. We contract things and integrate over these points which move in M. And in the end, there are some points which are not moving, and that will give us somebody who is in the differential form on configuration space of the endpoints. If there's just one point, so there may be more of them, but I don't have enough space there. And we are using GN, and that thing is closed. So D plus delta 30. Allenberg differential of this n is equal to 0. Something of this form. So this is what one would call the BV quantization of Chern-Simons theory, perturbative BV quantization. And it gives these forms on.
So here there are already two types of vertices, and some of them are integrated out.
Yeah. We integrate over those trivalent vertices, and there are the arbitrary valent vertices, so who are the external vertices that are not being moved, that are not being integrated over such and such.
Sorry, this equation is for each graph?
No, it's the sum of these things.
Of which graphs? All graphs?
Of,
and some of them equal or something?
Okay. Yes, it's the sum over all trivalent graphs which are trivalent at the internal vertices, ambivalent at those external vertices. We take these integrals. We take the sum of those things, and just if n is fixed, so here n is equal to 1 because of this one. There is this usual whatever 1 over the number of automorphisms of graph and the things like that. Okay, so that's this kind of introduction story for what this perturbative Chern-Simons looks like, and I already managed to confuse you here, so I'm really glad. There is just one little thing, that to make these integrals actually converge, and to make sure that all those Stokes theorem works everywhere as it should, there is a little technical trouble. It is that this P should actually be a two form on the configuration space of 2 points on M, but compactified, or is some kind of real oriented block. Compactification, meaning that when 2 points in M are actually getting close to each other, then in the end, what we will remember is the direction. So there are 2 points, they are numbered, they are distinguished. So there is always a sphere in the end coming from these collisions, which is glued into the sphere. And it's not just there to satisfy this, but also that P now restricted to the boundary stratum, so on the boundary of configuration space, which is the same thing as unit tangent bundle, sorry, unit normal bundle. That's probably a stupid notation for the diagonal M inside of M squared. That this should be how should I put it? So it should be the whatever area form on every sphere. So whenever those 2 points collide at some particular point of M, but in arbitrary direction, then our propagator should be of this form, where I now suppressed this thing. So it's just multiplied by the area form tensorically. There's
more boundary coming from the boundary of M, though. So you're just looking at one part of the boundary.
Okay, so let's suppose here that M is closed for a moment. Okay, so this is let's say this was the end of the whatever introduction of what was done before. So this is how it here's how it's done with this with the perturbative Chern-Simons. Now the question that I want to look at first is how to reconcile those two pictures. In some sense, that here M is closed. I confused everybody by not saying that M was supposed to be closed. Whereas here M has a boundary, and there is this current boundary condition. So now the question is somehow what would be perturbative Chern-Simons with chiral boundary condition. And it turns out that it is actually relatively easy. Let me look at the simplest possible example where M is only a three-dimensional ball, because there I can give you explicit formulas. Let's say that M is equal to 3, and so sigma is the boundary of M is 2 sphere, which will be CP1 as a Riemann surface. Now, what is that H thing? So what should we do? The thing is that instead of taking all differential forms on M, which is P3, we should take only those that satisfy the boundary condition. So there will be a restriction which goes to differential forms of CP1. But here there is the space of forms that with our boundary condition, which is omega 1, 0, CP1, and plus omega 2, CP1. Okay, and here is then the space. Let's call it chiral. Space of forms that satisfy the boundary condition. And then this is going to be our complex. That's where we're going to work now. It's a nice thing because this thing is actually acyclic. So I don't have to worry about the vanishing, non-vanishing cohomology, but I ignored over there. It's acyclic. I can provide you an explicit H, which goes from this thing to itself. And it's given by a kind of cute formula or a cute picture, if you wish. So we'll need that form. P will be a two form on. It's not really compactified because it's still non-compact, but kind of a completed configuration space of 2 points on B3. It's only like when 2 points are colliding, then we are adding that sphere, but those points can still go to the boundary of B3, and then we just do not add anything. So that's the thing. And what it looks like is that if you take 2 points, 1x2, that's B3, then we can take the hyperbolic geodesic B3 passing through those 2 points, and it will give us as a projection 2 points on the boundary sphere. So that's that one. So that's R, which is a projection going from configuration space of 2 points on B3 to configuration space of CP1. It works with a bar. So there is no more.
Thinking of it, the geodesic, like you think of it, what geometry there?
The hyperbolic geodesic, so it's just the arc of a circle altogether. Sorry, but this picture is sort of not three-dimensional enough to make justice to that thing. But yeah, you just take the circle.
On the right hand side, do you also need some kind of compactification there?
No, there's no. The compact. Okay, it's not really compactification. It's just this completion is only happening inside. So whenever 2 points collide in B3 inside of B3, then there is a additional sphere. I mean, this direction is remembered.
But you don't do anything for points that are, I mean, also on the boundary points can
Right. So
but there you don't compactify.
no, there I don't do anything.
But there are no geodesics with ends at the same point. There
That's
are-
true.
Yeah.
Yeah, thank you. That was the right way how to unanswer your questions. Okay, so things that here there's actually a nice invariant to form. I will simply write it in coordinates if you wish. So is this Z1, Z2 over this guy, but it's somebody who has geometrical meaning, and it is in particular SL2 invariant. And whatever it would be, whatever the 2-point function for whatever, if you have two currents, something. Anyway, and so that our propagator is simply the pullback of this guy. Maybe there is some 1 over 2 pi I or something. And oddly enough, or not oddly enough, it works. That's the thing which is not entirely, or it is really simple. That if we take these 2 points and make them collide and look at all possible directions how they're colliding at 1 point in B3, we're actually getting the pullback of this guy is actually the area form on the sphere, but it's still. And it has it just works. So this would be now a perfect start for the actual talk in this kind of a meeting where there is field theory and topology, because that was field theory, and now the perturbative Chern-Simons used or had been used a lot in topology for providing not invariants, and this would be maybe a nice way how to relate maybe conservation integral with what tau, so invariant. So, but unfortunately, that's not what I'm going to do, because I promised you that I will do some physics. So let me.
So that propagator is it by chance can it be thought of as a Hodge propagator for some particular choice of metric inside the ball?
I don't know. I even don't know exactly precisely how to. There was this trouble of fighting with the boundary condition.
Yes. Yeah.
And it was not clear how to impose this Hodge thingy so that it would somehow lead to the boundary condition.
Yeah. Yes.
But yeah, of course, we were trying to do all those stuff until just one should go to kindergarten and write down a formula.
Yes.
And so this cheating approach of just writing down a formula simply works. Maybe like an exercise for the audience, or that is that complex is acyclic. Similar complex is acyclic if we take a handle body. So it's still whatever, because whatever holomorphic differential is uniquely defined by its A periods or something like that, and the same type of complex secret for arbitrary antibody. So you can try to find the propagator in that case.
So Pavol, in higher dimensions, you could have taken any conformally invariant volume form on a sphere and done this on a hyperbolic ball of a higher dimension. Is there any, like, has that propagator been observed before? Is there an interpretation to that? Because you get a different degree operator, but.
I mean, it's a. You should also answer your question. But yeah, it's like part of what would be the program, even though its program is rather modest, to go with to higher dimensions with this. So this thing, I mean, if there is still a bit of time, I'll tell you at least like what the questions are. Okay, so what am I going to do? As I said, I should be really now doing perturbative Chern-Simons with chiral boundary condition, but I will not. But I'll be using the same propagator, which I will call, sorry, I'll call it P0 because there is no real algebra inside here. I will be using the same propagator, but for a slightly different boundary condition. Let me say why it's possible. So there is some kind of mixed chiral anti-chiral boundary conditions. And it works like this. So we imagine that we split G into direct sum of two vector spaces, not just vector spaces. What is the only thing that is needed is that V minus is the orthogonal complement of V plus with respect to the K. And the boundary condition that I will take is that we will have in the boundary we'll have 1,0 form, but with values in V plus 0, 1. So it's vice versa. So it's 0, 1. Introducing V plus. So now the boundary condition is that when A goes to the boundary, A at the boundary is in here. There is a V minus component, is a 0, 1, 0 form, and V plus component is a 0, 1. And it is actually for any possible perturbative reasons, this is a good boundary condition. Now, to make it for as it was here, to make it a BD story, I will add there also two forms. Sigma that is in G, there is no restriction, and there are no 0 forms, which corresponds to kind of killing the gauge invariance, similar ways possible. Anyway, this is our complex now.
I just realized I'm really confused by the first board.
Yes.
So the Lie algebra is a compact Lie algebra, so it's real, and yet the boundary condition is complex. How can you have complex boundary conditions for a real form?
Because you're Witten.
Okay.
You can say that you're not Witten, but
right. But I mean, now you're a true boundary. Now you're us here on this last board. So I'm wondering. I'm trying to understand: is V a real or a complex vector space now?
Sorry. So here, okay. At least here I can be fully specific.
Yeah.
So here this G has an inner product, which is not, but which is inner product in the sense that it's not necessarily a positive definite. It's just not degenerate at this point. So this is no longer compact Lie algebra. We are just purely perturbative.
But it's still a real vector space.
But it's everybody here is real. these people are not real.
Yeah.
As they are written. Now, the way around, whatever, if you do it, the right physics way, meaning not doing the weak rotation, but when the conformal structure is actually pseudo-conformal structure, things like that, and everybody is staying real. But then there is this wicked rotation, which makes everybody complex. And frankly, it's an easier thing, maybe.
So you want the boundary to be Minkowskian?
Yeah, okay.
As if.
It's as if Minkowskian, but then in reality it is then Euclidean.
Okay.
But I mean, this is a trouble which is there already for me in Wezumino Witten. This model just makes no sense because it's the whatever Lagrangian whatever the action function is complex.
Yes.
But if you're in the whatever Minkowski setup, then it's perfectly real. Everything is real. But then if you actually do want to do anything, you have to do that rotation, and then things are complex, and then here we are. Whatever contour in which we choose in when we're doing path integral, anything.
You answered my question perfectly.
Yes. So, by the way, how much time is it a 1 hour talk or 50 minutes or?
It's 1 hour talk.
It's 1 hour.
So we have 29 minutes.
Okay, yeah, cool. So, okay, so let me get the So this is a perfectly good boundary condition. So what does perfectly good mean in this sense? It's one thing that one can say that this is it's a DG and right, that it's not important here. Lagrangian manifold in the space of boundary fields. So it's an omega sigma G. If I do it that way, I should put there shift by 1, but let's ignore all of this. But which simply means that it's a in this setup it's a DG Lie subalgebra in so if you write it like that, omega G. This is a G subalgebra, which is Lagrangian with respect to the pairing that we have there. And so this is one thing. What is good about boundary condition? This would be sort of basic classical thing to say, but there is one more thing which one should say, and which still works here. Namely that it is this boundary condition is an elliptic complex. It is still an elliptic subcomplex of this guy. So these are just some general words that I would use for what would be a good boundary condition in Chern-Simons or in similar theories in AKSZ models. It should satisfy this obvious condition, and it should satisfy also this obvious condition. This obvious condition is used to be like for finding a propagator. If you want to have a propagator, then we should find this kind of contracting homotopy, roughly speaking. And for that, we should really have an elliptic complex. But anyway, here it is true. We actually do have already a contracting homotopy. Here, the propagator.
What does exact mean?
Exact Lagrangian, meaning that we have a symplectic manifold of all fields, this BD manifold, which is actually exact symplectic.
Okay.
And yeah, then what we should have that when you take the one form and restrict it to the Lagrangian submanifold, then that one should be exact, and actually it should be D of some given function. And that given function is going to be the boundary term coming to the action functional. But here the given that function is just 0, so we're not adding anything to the Chern-Simons action functional. Okay, just this. Anyway, what is the propagator? We simply need to take this one is P0, and apply it once here and once there. So it will be P0 tensor projection onto B minus, and plus complex conjugate P0 bar projection to projection to B minus and it's to B plus. This would be a propagator in that sense. Then now we can start doing our perturbative nonsense. So we have a propagator which is given by the sum of two things. No, like this. Let's say T plus, it really lives in something like D plus tensor D plus and D minus. It's in D minus. Say D minus. And those are the two parts. So D plus D minus is the contravariant in a product. So now when we start computing whichever diagrams, something like that, so we'll have trivalent vertices. So there will be points that move inside our ball, and we're putting the propagator over each edge. But that propagator splits now into sum of two pieces, so it's better to actually choose everywhere a sign and write it as that we're now taking the sum over all possible diagrams, where each diagram actually is coming with a sign on an edge. So such a thing then nicely decomposes into a re thing and into a form thing, because everything is a product. So you can imagine that. Sorry, I should have called this probably B minus. Yeah, this one is B plus. So what would be the thing? It will be P minus, P plus, etc., whichever our choices were. It's a purely P thingy, and in the end, where it has values, it belongs to some tensor power of G. And then there's some form thing. P minus contains P0, here we have P0 bar, another P plus is P0 bar, etc. So this is just a form of configuration space of endpoints. And we need to take some of these things. It should be computable in principle. I mean, this is very easy to compute. We just put structure constants everywhere and then put those orthogonal projections everywhere. Compute a thing which is in the tensor power of our real algebra. This is in principle computable. That we put there those explicit formula for P0. But what happens is that it's physics, so things start diverging because I didn't care about what was happening on the boundary of the sphere. And there is no way out of this. It actually will diverge. What is the whatever one loop? One of the divergent part of this. Well, all right, but how should we understand it? No, this where was it? This original Chiral boundary condition is very nice because it actually is a conformal boundary condition even after we quantize it, or can be defined in such a way. Whereas this mixed boundary condition, it's as it's written, it pretends to be conformal. It only uses the complex structure. But as it all often happens in perturbative condensation, such things don't survive. Once we start with using some regularization or things like that, and it will not stay. It will not stay conformal, and it will show up as some divergences. So how should one deal with this? To deal with divergences, we need to regularize things, so we need to modify our propagator. Modify. Where is the trouble? The trouble happens when Z1 and Z2 start colliding. When these 2 points become the same point, there is a divergence happening here. And it will show up sometimes in the integrals. So what we can do, we can simply prevent those 2 points from colliding. Simply say by multiplying this omega by some cutoff function, which is 0 whenever Z1 and Z2 are too close to each other. So that, I don't know, one can write is some omega whatever of G. So this will be omega times Hg, where this H, a Heaviside function, it is defined in such a way that this G is a Riemannian metric on S2 with the given conformal class. So conformal. Conformal class. One. So it's just the standard metric times some function. And we simply say that whenever the distance, if this distance between I'll step with it, that Hg of Z1, Z2 is equal to 1 or 0. That's if the distance of Z1 and Z2 is at least 1, and this is if not. So if they're too close, then we just skip it. It's a very cheap thing to do. What we then have to do is then multiply our metric by a larger and larger number and try to take the limit, which doesn't exist, but at least try to look at the asymptotic behavior. And that's what you should do. Okay, so that's I should be still able to do. So now I can tell you that the only divergent is this taking one particle irreducible diagram. Is this one? Sorry, no, one loop. I don't know what's happening for higher loops.
You mean after you change the omega or?
Yeah, so whether I change omega or not,
Oh, no, okay, yeah.
I mean, when it goes in the limit, it goes to infinity or,
Yeah.
so the only diagram which diverges is this one. So at least we can think of why other things don't diverge. No, if I put two pluses on these arcs, I would have the same form there. It would be the same outer P0 or P0 bar there, but which is of such a form that the P0, wedge P0 is actually equal to 0. That's how roughly how it was defined. So we need to have plus and minus here. Now, why we need to have plus and minus on these edges? It's slightly less obvious, but one can say since the boundary condition is such that those minuses are 1-0 forms, then two 1-0 forms, if we wedge them, they will give us 0. If you really go to the boundary, and since the divergence is happening on the boundary, then we should only have like 1 plus and 1 minus. It's a hand waving thingy, but it actually works. And there is another, say the third thing is that anything with more than 2 external edges actually converges, which by the force of authority is true. So this is the only divergent thing, and to put it more precisely, it's like this, that if it, I don't know what's the right notation for this, so if you take this whole one particle irreducible quantum effective action, so I'll just that's effective quantum effective action, and only one loop. So there is, okay, one loop is implicit of A, but we need to choose that, we need to use that regularization, otherwise it diverges. So I will write here, it's epsilon times G1, one metric, and we can do the same thing, epsilon times G2. Same epsilon, which is just a number, positive number, but G1 and G2 are 2 metrics, so 2 ways how to take the limit. Epsilon goes to 0. So this is hopefully a mathematically precise statement that we are actually taking these things which exist and taking the limit, and that the limit exists. The outcome is there is H bar, which for the moment, H bar was not introduced, but it is there, divided by 4 pi integral. There is a boundary term. It's coming all from the boundary. The divergence is coming from the boundary. There is a logarithm of G1 divided by G2. That's a function because they are the same conformal class. It's a well-defined function. And times a 2 form. And who is the 2 form? The 2 form is that when you take the B plus part of A and then this way, I don't know. Plus, minus, okay, but not like that. So this is let's say thing which belongs to G. So G, I can put those brackets here. something like that. Then we just contract this A plus form has values in V plus, that A minus has values in V minus, and we contract it using this operator living in G tensor. Anyway, so what it means is that, let's say, the one loop condition for that boundary condition actually being conformal. And only if this thing like this. Tensor G. That thing which should supposed to vanish, should be vanishing, is actually called something. This is the generalized tensor. Of this equation of G equal to V plus V minus.
What's the word after Ricci?
Ricci tensor.
Tensor.
I have something we can run in triple, so would it vanish?
Running triple is not a situation like that. You see, there was this this orthogonal decombination.
Well, generalized just because it's not positive definite, or
It's generalized because it's not Ricci tensor for the moment, because there is no Riemannian manifold. But okay, so just two final things. So why is it actually generalized Ricci tensor? So for one thing, one can generalize this story easily to something which is called courant algebroid sigma model or courant algebroid models. So what is happening there, just for in case you made such a thing, so we have still this kind of nice trivalent vertices which correspond to courant bracket here, but there is also another type of vertex. Which corresponds to the anchor map. And there are different type of vertices, different type of fields. One can say that there are those sections of courant algebroids, but there are also positions and momenta. So that's where these things come, of course. And if one does the same thing there, one obtains similar picture for the divergent thing. But there is some little correction. It's not very important. Exactly. There's still plus minus. Here's plus, here's minus. There is 1/2. And this loop coming back, it means that now we're differentiating those structure functions, which are no longer constant but functions. And this is still what is called the generalized Ricci tensor, but in case when our courant algebra is actually exact, this is the true Ricci tensor. Generalized. Or not. But when when the current algebra is exact.
Sorry, this is a current algebra on what?
Anywhere. So just in place of G of the Lie algebra, I'll take the current algebra.
So
Some
now you have an auxiliary manifold on which the current.
yeah, it's just some completely different manifold which has not appeared yet. And so just to finish with what was the why would one ever study such a question? The motivation. But when we take Chern-Simons on a sort of sandwich, so it's a on sigma times interval. So then we have two pieces of boundary, so we should introduce should put some boundary conditions to make sense of it. And if here we put that V plus V minus type of boundary conditions, plus V minus boundary condition, and here we put something that would look like a topological boundary condition. So here we impose our fields to have values in some H, where H part of G is a Lagrangian algebra. So we have a Manning pair, if you wish, something of this form. So a statement is that this kind of sandwich model, where there is some classically conformal boundary condition, there is classically topological boundary condition, and this is equivalent to a two-dimensional sigma model for maps from sigma to G mod H, with some nice particular Riemannian metric here and some particular closed tree form here, which can be constructed out of this picture. And the thing is, this was my childhood project, maybe these kind of things, when I was doing my master's thesis, and I don't know when. Roughly speaking, what's happening here that all the interesting stuff is coming from this V plus V minus. This is a sort of topological-ish thing. So all the dynamics is happening on this top part of the boundary. But here this target depends on H quite a bit. So what this is called, so I'm choosing different H's. This is called Poisson-Lee duality. Namely that these rather different looking two-dimensional sigma models are basically the same thing. The statement is not quite that they are really equal, unfortunately, unlike for the usual duality. The statement is only that they are equal modulo something that looks like a topological boundary condition. Okay, sorry, this derailed a bit at the end, but that's the end. Thanks a lot.
Questions to the speaker?
Yes.
I have two completely different questions. I'm being very greedy. So the first is, you had SL2C, since you mentioned the SL2C invariance of your, so your cutoff, of course, is only invariant under isometries.
Yeah.
And typically one would use BRST or BV techniques to rescue. So you don't care that the cutoff breaks the symmetry as long as you can restore it using ghosts. Do you do that?
No. I mean, I'm not saying that I don't want to do that. I just just for this for this one loop thingy.
Oh,
there was no.
you just had one graph.
yeah, there was no need
And
to,
you were able to
but for
verify at the end.
but for doing it for the real, yeah, we should.
That was first question. And second question is, if G is no longer simply connected, do you get anything,
Where?
capital G,
You mean here?
Yeah.
Here or
everywhere?
it's
So now, for example, instead of a Lie algebra, you would have a bundle of Lie algebras, things like that.
I don't know. Like in the perturbative story, as I presented it, there was no group ever.
Well, there is now.
Yes.
That's why I'm raising it.
Yeah, I understand, but it's somehow the way I was presenting it doesn't matter. I'm not saying that it really doesn't matter. It's just in the way that I presented it. Yeah, I mean, this perturbative story was around it was where zero, yeah, around zero. So there was nothing that could happen.
So in higher dimensions, do you have a candidate for natural shifted Lagrangians to choose in your shifted symplectic guy?
Okay. Now that's in principle that's relatively easy. You see the simplest where was it? Anywhere I can. You can always just use what are the hot star for imposing it, and so one natural thing is to that we go up to the middle. So with everything all over degree we set equal to 0 in the same way as it was maybe here, or where is it? That there are no 0 forms. And then when say if the boundary is even dimensional, then we take solve dual forms or something like that in the middle, and then above we admit everything, and one can play with this kind of boundary condition in many possible ways.
Any more questions? So does this give some, like this different boundary conditions, does it give some invariance of 3 manifolds?
Okay, for this it's way too far from such a thing, and I don't think so that it will ever happen. What should be investigated a bit more is purely that chiral boundary condition from this perturbative point of view.
Mm-hmm.
So I still don't think that it will give a new invariance, but it might. The one little hope is that it will say that both Taub's anomaly is equal to 0. The thing like where there are 2 ways how to define basically perturbative Chern-Simons, either using an associator or either using these integrals, and it's not yet clear whether those 2 things give the same outcome, and this might hopefully prove it.
So let's think Pavol again. We have a coffee break upstairs, or in the where it was before, and we'll reconvene at 11.